Late August 1944. Observation Post 4, Sparrow, France. The officers of the Flak 155W Regiment consulted their reports in incredulity, unable to comprehend the numbers that defied every principle of ballistics they had learned in the Luftwaffe. Every graph, every statistic looked ridiculous. The V-1 flying bombs dropped toward London were shot down at rates that German physics declared impossible. General Max Utel, in charge of the offensive, kept his countenance steady, but inside he felt the restlessness of someone who watches the impossible become routine. The initial arrogance, the certainty of the invincibility of his weapon of revenge, began to dissolve in the face of something that could not be calculated or predicted. That German laughter, that blind confidence in the perfection of his calculations and the lethality of his creation, was about to be silenced. Behind the smokescreens and seemingly magical statistics, an unseen organized force operated. American engineering on an industrial scale, combined with cutting-edge technology and meticulous planning, turned every VT fuse into an instrument of precise destruction. What the Germans called the invulnerability of the V-1 proved to be vulnerability in the face of something they could never imagine. In this video, we will explore the story of the day when 82% of V-1s launched against London were shot down without the enemy knowing how, revealing the power of mass production, applied engineering, and American industrial innovation. What seemed impossible became devastating, and the war for an instant quietly changed course in the hands of millions of anonymous operators. But before we dive into the details of the campaign, there is one statistic that defines this whole story. In a single day, 82% of the V-1s launched against London were destroyed before they even touched the ground. While the Germans relied on the accuracy of their weapons and the efficiency of their calculations, an invisible, silent, and organized force operated behind the scenes, mass-producing VT fuses, combining advanced engineering, impeccable logistics, and radar technology that turned every shell into a sentence of failure for the weapon of revenge. Imagine thousands of devices fired and shot down with near-perfect accuracy, without the enemy even understanding what was happening. If you value detailed history and want to follow how science, industrial production, and human ingenuity changed the tide of war, please like and subscribe. This allows the channel to continue bringing these incredible facts to light, connecting you with the details that history books rarely reveal. August 1944 brought palpable tension to German observation posts off the coast of France. In the Flak 155W Regiment, officers and technical engineers studied reports, trying to decipher numbers that defied their comprehension. Each V-1 launched seemed to meet an uncertain fate, exploding or being shot down before it hit London, and no one in command could explain how this occurred. Max Utel, the regimental commander, maintained the discipline of his staff, but each intercept report added to the unease. The proportion of V-1s destroyed by anti-aircraft fire rose from 17% in June to more than 74% by mid-August, figures that seemed to defy all German military experience. Meanwhile, in England and the United States, command centers quietly celebrated the power of industrial mobilization. American factories produced tens of thousands of proximity fuses daily, each tested and calibrated with near-mathematical precision, while engineers perfected tracking radars and smart munitions. The contrast could not be more evident. On the one hand, German craftsmanship in laboratories and limited assembly lines. On the other, synchronized mass production, supported by decades of investment in applied science and technology. In a moment of revelation, the Germans ignored that American production of VT fuses was approximately 10 times greater than any German industrial capacity, a colossal difference that no one in Berlin could measure. If you were surprised by this statistic, leave a word in the comments that summarizes it. Absolute power, unbelievable, shocking data, or logistics wins. As the days wore on, Tell and his officers tried in vain to adjust tactics. Changes in altitude, safe from firing, night launch times, everything seemed insufficient. Each attempt to adapt revealed the insurmountable distance between German technology and the American industrial war machine, creating a scenario of growing frustration. French observers, hiding in makeshift trenches, recorded V-1s being shot down with lethal accuracy, while British pilots themselves reported synchronized artillery bursts, as if each shell knew exactly where and when to detonate. A sense of powerlessness was growing in the German command centers. The weapon of revenge, built to subdue London, was being dismantled not by enemy strategy, but by an invisible system of production and engineering that they could not comprehend. And even in the face of all this evidence, no officer dared to admit that defeat could be inevitable. Each report was examined, re-examined, and the search for internal errors continued. But beneath the surface of the German confusion, an invisible logic was beginning to unfold. American engineering not only mass-produced but turned every unit into an efficiency multiplier. Every VT fuse, every calibrated shell, every tracking radar worked as part of an industrial precision mechanism, achieving a rate of destruction that, until then, the Germans had considered impossible. American production lines knew no rest, while German analysts remained stuck in their scientific tradition, underestimating the speed, scale, and coordination of enemy logistics. The contrast between theoretical calculation and operational reality became a cruel irony. The weapon of revenge, a symbol of German supremacy, was defeated by a combination of meticulous planning, applied technology, and invisible industrial discipline. And so, as Wutel jotted down yet another line of inexplicable faults, the German expectation of an effective attack against London quietly unraveled, setting the stage for a turning point that no one at that observation post could have imagined, but which would forever change perceptions about industrial power in modern warfare. The design of the Fiesler V-103, which would become known as the V-1, the flying bomb, was, by German standards in 1944, the epitome of effective military engineering, cheap, lethal, and psychologically devastating. Powered by an Argus AS-109-014 pulse-jet engine, its simple structure concealed a strategic purpose. With 850 kilos of explosives, a cruising speed of 640 km/h, and an average altitude between 600 and 2,700 meters, the V-1 had the mission of paralyzing London, breaking British morale, and forcing the Allies to redeploy their defensive resources. It was, in German logic, the perfect weapon. Pilotless, difficult to intercept, launched en masse from the occupied European coast. The cost of production was almost symbolic by the standards of the war, about 5,000 Reichsmarks per unit, equivalent to a fraction of a manned bomber. At Pinneberg and Peenemünde, engineers designed its trajectory and control based on mechanical chronometers and gyroscopes, believing that accuracy was not essential as long as the psychological impact was guaranteed. Major General Walter Dornberger, one of the program's leaders, calculated that even if only 25% of the flying bombs reached the target, the volume of explosives dropped would surpass that of the 1940-41 Blitz. The math seemed unbeatable. The numbers were in favor of the Reich. The confidence was absolute. Within the German military apparatus, there was no doubt. The Allies had no way to stop the coming wave of destruction. Ballistic evaluations indicated that British fighters would have to reach speeds in excess of 650 km/h to reach the V-1, risking only 200 meters from the target, enough to be hit by the explosion itself. Conventional anti-aircraft artillery, on the other hand, with timed fuses, had to predict trajectories, calculate flight time, adjust the firing, and hope that the target would cross the lethal field at the exact right moment. For German calculations, the chance of success of a conventional anti-aircraft projectile was less than 0.01% per shot, that is, less than one hit per 10,000 rounds. It was statistically insignificant. The Reich was betting on mathematics, and mathematics, it seemed, was on their side. This belief in the supremacy of war logic was reinforced by German technical ideology, the conviction that technological excellence surpassed any crude effort of mass production. While America multiplied its factories, Germany bet on punctual innovation, on weapons with a revolutionary effect. The V-1 was the culmination of that mindset, an elegant, straightforward, devastating project. On paper, nothing could stop him, and the first releases seemed to confirm this. At 4:25 a.m. on June 13, 1944, just a week after D-Day, the first V-1 crashed over London, destroying a railroad bridge at Bow. 6 civilians killed, dozens injured, hundreds of houses damaged. British newspapers mentioned the strange sound in the sky, a pulsating engine that suddenly disappeared, followed by a brutal explosion. It was the beginning of the campaign of terror. Over the next few weeks, more than 9,000 V-1s would be launched from ramps in France and Belgium, with thousands more being carried by Heinkel He-111 from medium altitudes. The prediction was clear. If the launch pace was maintained and the Allies failed to create an effective defense system, London would become uninhabitable in a matter of months. The production was intense and relentless. Although the Reich was already under pressure from all sides, it allocated resources, infrastructure, and labor, often slave, to keep the underground factories operating. The Mittelwerk, a complex underground facility beneath Konstein Mountain, was churning out V-1s at a steady pace, powered by prisoners in subhuman conditions. The strategic urgency justified any sacrifice. The calculations remained inflexible. Even with failures, deviations, and losses, statistical efficiency was still acceptable. Dornberger remained confident. Goebbels praised the new weapon in his speeches. And Hitler, convinced that London would be destroyed by the technology that symbolized his revenge, ordered increases in the pace of launch. But while Germany calculated margins of error and acceptable losses, Britain reacted in silence. The Anti-Aircraft Defense Command, under the leadership of General Frederick Pyle, began to redesign the entire defensive structure in the south of England. New radars, repositioning of artillery regiments, and above all the introduction of a carefully guarded technological secret, the VT, variable time fuses, an American invention based on miniaturization of radio circuits, extreme mechanical strength tests, and a production chain that involved more than 110 factories in the United States. The device detected the proximity of a target and automatically detonated at a lethal distance. It was not necessary to hit the flying bomb directly. It was enough to get close. It was what would turn an impossible statistic into a routine operation. The German error of judgment was twofold. They underestimated the speed of British adaptation and completely ignored the reach of American industrial power. In the technical mindset of the Reich, the Allies possessed neither the scientific precision nor the mechanical ingenuity to develop something as sophisticated as a fuse, which could think for itself. Such an artifact, in the view of the German engineers, would not withstand the G-force of a shot, the heat, the rotation. It would be necessary to miniaturize transmitters, batteries, valves, and sensors in a tiny space, and still ensure that the device withstood storage and worked instantly. For them, it was fiction, and so they never considered that possibility. But the United States didn't just consider it, they made it work, tested, they standardized, and they produced by the millions. By the end of August, the result of this German arrogance and American quiet strength was beginning to manifest itself. The interception rate jumped from 17% in June to 40% in July, and then to 74%. In a single day, it would reach 82%. A proportion that defied German intelligence reports, leading Wtel and his officers to assume sabotage or internal flaws in the V-1 design itself. But the problem was not with the weapon, but with what the Germans refused to imagine, that their enemy not only knew what he was doing, but doing it on a scale that was impossible to comprehend. In the next part, we'll follow the German command's first desperate attempts to understand what was going on, and why. Despite all their calculations, the V-1s kept falling before they even crossed the skies over England. In early July 1944, the pattern began to break. Each day more V-1s disappeared from German radars before reaching their targets. Along the French coast, technical observers reported explosions in the air, often far from visible anti-aircraft batteries, other times suddenly appearing in the sky with no fighter nearby. The flying bombs were not being hit by direct hit, nor were they entangled in containment balloons. They were simply being destroyed in mid-flight, as if the very space around them had become hostile. The command of the Flak 155W regiment reacted with bewilderment. The reports delivered to Max Wtel suggested that something fundamental had changed, but the known parameters of ballistics offered no reasonable explanation. Based on the current calculations, the chance of a direct hit with conventional shells was statistically negligible. Artillery science said that this was not possible, and yet it was happening before their eyes. The first response was technical: review the data, recalibrate the instruments, consider internal failures in the V-1s. Some officials hypothesized sabotage on the production line, suggesting that critical components could be failing during flight. Others were suspicious of atmospheric changes that were altering the trajectories. But none of these explanations withstood the growing volume of failures. The pattern was too broad, too constant, and most intriguingly, field reports showed that V-1s were destroyed with no visible signs of impact. In many cases, explosions occurred meters away, in mid-air, as if the anti-aircraft shells knew where the targets were. To a mind trained in German physics, this bordered on the absurd. The meetings became daily. At V-1 headquarters, engineers and commanders gathered with their eyes fixed on maps and charts that did not fit any logical model. The impact sites disappeared. Estimates of success dissolved. WTEL demanded answers, but his experts had only assumptions. The number of bombs destroyed grew without an explainable curve, without a controllable factor. British efficiency was increasing irregularly, but undeniably, and that, for a war machine shaped by order, statistics, and control, was intolerable. A bolder theory began to emerge. Perhaps the British had developed a new type of radar, capable of tracking V-1s more accurately. Perhaps a new artillery doctrine was being applied, combining multiple batteries in sync. But even these hypotheses did not explain the accuracy of the explosions. The videos captured by reconnaissance airmen showed disconcerting scenes. The V-1s crossing the channel at constant speed, and suddenly, a wave of detonations in the air. No impact, no touch, no approach. Just a sudden explosion that destroyed the projectile. Witnesses on the ground saw the flying bombs shattering hundreds of meters from the visible defenses. It was as if the sky was reacting on its own. The traditional doctrine of the Luftwaffe, which until then had governed all missile feasibility analyses, was beginning to unravel. The technical team's own calculations, based on probability and mathematical models developed over decades, could not keep up with the pace of losses. In just 3 weeks, the interception rate jumped from less than 20% to almost 40%. And then, even more surprisingly, it exceeded 50%. No weapon in history had lost its effectiveness so quickly in the face of conventional defenses, and that was precisely what confused Berlin. There was nothing conventional going on. General Beutel, in a memo sent to the High Command, classified the phenomenon as a ballistic anomaly, not explainable within the limits of known weaponry. He recommended an urgent reassessment of the launches, but also reinforced the maintenance of the campaign, stating that the psychological impact of the V-1 was still relevant. But behind the scenes, internal reports were beginning to indicate that the system was collapsing. Every day, fewer bombs crossed the English coastline. In London, air alerts became rarer. In contrast, Allied gunners reported something extraordinary. Their hit rates increased over time, even without changes in training or ammunition, at least none visible. When questioned, they said only that they were receiving special projectiles. Most did not even understand how they worked. They only knew that they worked. On the German side, engineers were instructed to repeat tests with V-1s over Reich territory, away from the British coast, to see if the problem was technical. But in internal tests, the flying bombs behaved perfectly. No glitch, no early explosion, no unexpected deviation. The conclusion was disturbing. The problem only manifested itself when the missiles were launched at the United Kingdom. This eliminated flaws in the project. There remained, therefore, something external. But what? The question resounded through the corridors of German intelligence and engineering, like a disconcerting echo. What was happening in the English Channel that turned a precision weapon into a useless piece of metal? The answer, still invisible to them, lay in the basements of American factories, where miniaturized circuits, radio sensors, and vacuum tubes were assembled by thousands of anonymous workers. The weapon that silently destroyed the V-1s was already operating at full scale, but it remained as secret as it was lethal. And as the Reich's brains dipped into formulas and statistics, the next wave of intercepts would prove that German mathematics was about to be rewritten, not by equations, but by applied engineering. In the next part, the story moves inside the backstage of this invisible revolution. American industry that secretly produced the most effective technology in war, without its enemies even knowing it existed. Realizing that the losses of the V-1s were becoming systematic, the German High Command activated a technical task force to understand the nature of the problem. The best engineers from the Luftwaffe and the Heereswaffenamt were called upon to analyze the performance of the flying bomb and propose countermeasures. Tests were conducted over Reich territory, where the V-1s worked perfectly, following trajectory, altitude, and programmed explosion without any failure. This confirmed what some had already feared. The defect was not in the bombs, but in the conditions in which they faced the British defense system. The hypotheses multiplied. Tests were conducted with altitude variations, from launches at 600 meters to flights above 3,000 meters. Attempts were made with night launches, low flights, simultaneous bursts with dozens of V-1s. No tactic offered significant change in the pattern of losses. The lethal behavior persisted. The English sky seemed to see the bombs. It was as if there was an invisible field reacting automatically to the approach. Intelligence analysts, limited by Reich technical dogma, insisted on explanations based on human error, sabotage, or atmospheric interference. None of them could even conceive of the idea of a fuse that would detonate by proximity detection. Technically, this concept was treated as unfeasible. Sufficiently sensitive radio receivers would not withstand the 20,000 Gs generated by the firing of the ammunition. Vacuum tubes would break. Batteries would not survive years of storage. Micro-components would fall apart in rotational acceleration. For German engineering, it belonged to the field of science fiction, and precisely because it seemed impossible, it was ignored. The irony of this story is that the solution was before them, but their own cognitive limits prevented them from seeing it. If you're enjoying unraveling these little-told facts of World War II, show your support. Like and subscribe so we can continue to bring you detailed analysis like this. As V-1s continued to be shot down by shells that seemed to have a life of their own, reports from the technical sector became increasingly evasive. Max Dubutel even requested on-site inspections of the British anti-aircraft batteries, which of course was unfeasible in the middle of the war. Frustration was piling up. No sign of sabotage in the factories, no structural flaw in the design, no logical conclusion that would explain the upward destruction curve. The engineers suggested, finally, changing the parameters of the V-1's navigation system, looking for more unpredictable trajectories. That didn't work either. Intelligence suggested changes to the launch time based on British operating patterns, once again without result. It was as if the enemy knew exactly where to aim in any condition. Meanwhile, the United States VT Fuse program was already operating with tens of thousands of units produced daily. More than 100 factories distributed in different states manufactured components with meticulous precision. Each batch underwent multiple quality tests, and even the workers responsible for assembling the components didn't know exactly what they were creating. The compartmentalization was total. Each section of the supply chain knew only its function, and that made the secret even more impenetrable. Compared to the chaos into which the German summit was plunged, the United States had turned science into a product of war. Sylvania electric reinforced vacuum tubes, delayed activation chemical batteries, and micro-transmission systems were combined into a single fuse that thought and decided the optimal detonation moment. And this decision was made in fractions of a second, based on the reflection of radio waves while the projectile was still at high speed. None of this fit into the German paradigms. The belief in the technical superiority of the Reich prevented its engineers from considering that they were being surpassed, not by a more sophisticated invention, but by intelligent, massive, and standardized production. It was the ideological collapse of an empire that saw war as a game of technical genius, rather than coordinated industrial systems. And while the Germans fell into the trap of their own arrogance, London was beginning to breathe. Not by force of maneuver or strategic retreats, but because the enemy, who had invested so much in weapons of terror, was now being defeated by an invisible assembly line. What Max Dubutel would write in his diary in September would sum up the abyss. We are facing an enemy that we cannot see, and that thinks logically that we do not know. In the next part, we will enter the factories where this invisible enemy was forged. A secret American operation that quietly rewrote the rules of modern warfare. The industrial conversion of the United States during World War II was not just a war effort, it was a national metamorphosis. In 1942, the country was still producing home radios, refrigerators, valves for household appliances, small transmitters for civilian use. 2 years later, this ecosystem had become the electronic heart of Allied forces. Each day, entire factories were relocated to produce VT fuse components, while laboratories turned civilian knowledge into scalable military application. What made this process extraordinary was not just the technology, but the ability to combine it with mass production that was unprecedented in history. At facilities such as Sylvania Electric, Western Electric, and Crosley Corporation, thousands of workers performed millimeter tasks with near-surgical precision, even without knowing exactly what they were building. Each fuse contained a miniature radio, Transmitters, receivers, chemical batteries, and vacuum tubes hardened to survive the impact of 20,000 Gs and revs in excess of 25,000 RPM. It was advanced technology, but above all, it was technology replicated on a colossal scale. For each part, there were hundreds of assembly steps, multiple tests, and rigorous inspections. No device left the factory without undergoing electrical checks, simulated vibrations, and test firing. This made the failure rate less than 2%, something that not even the Germans, with all their obsession with precision, believed was possible in such a massified industrial process. The real strength was not in the isolated genius, but in the integration between research, engineering, and production. The VT fuse was the end product of thousands of minds and hundreds of institutions. University laboratories collaborated with heavy industries. Specialists in home radios redesigned circuits to survive war conditions. Women, who had previously sewn uniforms, now welded microscopic filaments that would determine the fate of enemy planes and missiles. Sylvania Electric dedicated all of its electronic tube research divisions exclusively to the VT program, manufacturing hundreds of thousands of miniaturized valves daily. It was a scale that Germany could neither match nor understand. Meanwhile, the Crossley Corporation was producing more than 5 million fuses during the war, nearly a quarter of total American production. At their peak, American factories were delivering about 40,000 VT fuses per day, a number that surpassed the total monthly German V-1 production. Every 24 hours, the United States was able to manufacture enough equivalents to neutralize weeks of German launches, and costs plummeted from more than $700 per unit in 1942 to less than $18 in 1945. This precipitous drop in cost represented American industrial efficiency transformed into a weapon of war. The Reich never had access to such conditions. Its factories, often bombed, operated with a lack of materials, improvised tools, and above all with forced labor, a fragile workforce, weakened and unable to sustain complex industrial processes. In Germany, a single engineer could be responsible for several critical stages of development. In the United States, thousands of experts oversaw each step, ensuring redundancy and acceleration of results. The Luftwaffe, which had proudly watched its country develop the first operational cruise missile, would never have understood that it was fighting not just soldiers and gunners, but an entire economic system that was converting scientific knowledge into military power with devastating speed. Radar technology also reflected this industrial supremacy. The SCR-584, produced by Western Electric, was an automatic tracking radar capable of tracking fast, small objects, something unthinkable just a few years earlier. It transmitted information in real time to the anti-aircraft batteries, which used M9 analog computers, developed by mathematician John von Neumann and Bell Labs. These computers calculated interception trajectories with a precision that no human observer could achieve. It was an integrated system: radar, analog calculation, artillery, and fuse, 4 pieces that, together, formed the invisible gear that would bring down the German weapon of revenge. At British defense posts, operators didn't even understand the full complexity of what they were using. Many believed they were just receiving better quality ammunition, without imagining the level of research and production that was behind each shot. The enemy, for his part, believed that the British were just better positioned their batteries or receiving more rigid training. They never suspected that the very nature of the projectiles had changed. For the Germans, the Allies were slow to innovate, dependent on quantity rather than quality. This distorted view was fatal. The United States had demonstrated that quantity and quality, when integrated, produced something totally different: a military-industrial system capable of multiplying the effectiveness of every piece, every shot, every second. And while the Reich was desperately trying to figure out what was happening in the English sky, the American war machine was quietly becoming more efficient by the week. The failure rate of the fuses dropped, the speed of production increased, and London, which should have been in ruins, was still standing. Records from the time show that Germany did not even have the means to understand how such precision was possible. Its experts estimated that to achieve similar results, they would need technologies that they would not master for a decade. But the war did not wait, and the United States had occupied the place that would decide the fate of the fighting, that of the factories, the assembly belts, the microscopic welds, and the metal valves that detonated with deadly precision. The final irony was yet to come, for what the Germans thought was statistically impossible was about to become routine, and soon, a single day would show the absolute collapse of the V-1 in the face of American engineering. The next part will reveal that moment. Throughout the summer of 1944, as German engineers racked their brains trying to explain the mounting losses of the V-1s, the United Kingdom quietly turned its coastal defense line into a veritable electronic wall. Led by General Frederick Pyle, the British Air Defence Command completely reorganized the defensive belt in southern England. Entire regiments of artillery were repositioned from the North Downs to the coast, forming a corridor of fire designed not only to defend London, but to eliminate flying bombs before they even crossed the horizon. Each artillery piece was connected to an SCR-584 radar system, an American innovation based on automatic tracking of moving targets. This radar, operating in conjunction with the M9 analog computer, provided the batteries with a precise firing solution in real time. It was the replacement of human intuition by automated mathematics. For the first time, an anti-aircraft defense system was able to accurately calculate the trajectory of a supersonic target and respond with compatible speed. The artillery no longer fired on luck. It would shoot for sure. But the real leap came with the projectiles loaded with the VT fuses. These munitions, equipped with small radio transmitters, did not require direct contact with the target. When they approached a flying bomb, the signals reflected by the V-1's metal body automatically activated the detonation. This transformed near hits into lethal hits. What once required tens of thousands of rounds per interception could now be done with fewer than 150 rounds. Effectiveness has skyrocketed. By the end of June, British defenses intercepted 17% of the V-1s. In July, this number jumped to 44%, and in mid-August, it would exceed 70%. It was practical proof that American industrial production was generating a multiplier effect. More precision ammunition, more tracking radars, more effectiveness every week. The V-1, designed to be cheap and uncontrollable, was being neutralized with a system that seemed to have been designed solely to destroy it. The coordination between radar, artillery, and VT fuses created a perfect kill zone. When a V-1 was detected by the SCR-584 as it approached the coast, the M9 computer calculated its trajectory and fed the firing solution automatically to the 90mm guns. Within seconds, a salvo of shells was launched. With VT fuses, it was no longer necessary to guess where the V-1 would be. It was enough to get closer. The sky over the south coast of England has become an invisible lethal field. Most V-1s did not even cross 40 kilometers within British territory. Many fell into the sea before reaching the coast. Luftwaffe pilots in charge of airdrops noticed that the explosions occurred in mid-flight, without visual contact with the defenses. It was as if the air itself reacted to the presence of the bomb. On land, Allied troops celebrated the results, but few knew what was really happening. Most gunners were unaware of the technical details of the shells they used. They just knew they worked. This willful ignorance was part of the secrecy effort. Each projectile was accounted for. Unexploded units were immediately recalled. Naval patrols guarded the English Channel to prevent any remnants of the technology from being recovered by German forces. And even the troops who used the fuses were given specific instructions not to dismantle them. The complexity of the secret was not only in the technology, but in the logistical capacity to hide it in the middle of a war operation. And all this was only possible thanks to the industrial structure of the United States. While Germany struggled to maintain its flow of V-1s, employing prisoners in underground factories under the mountains, America multiplied its weekly production with increasing stability, safety, and quality. It was a continuous gear. The workers knew what to do. The machines did not stop. The shipments arrived in Britain at precise intervals. And in the field, every part of this chain worked with the same relentless logic as the factory. The results were visible. On the field, British morale was strengthened. The population of London, initially terrified by the V-1s, came to trust the ability of the defenses. The shelters emptied. The alert system has been adjusted. Confidence returned. On the German side, the reports became increasingly alarming. The number of destroyed V-1s increased by the day, while engineers remained unanswered. Max Wittel himself, in a meeting recorded in the Luftwaffe archives, declared, "We are not facing tactics. We are facing something invisible. They're not shooting better. They're hitting everything. It was the surrender of logic to the effectiveness of a system that the Germans could not understand. Attempts to adapt the V-1 failed. Changes in altitude, alternate routes, night launches, nothing worked. The Allied system reacted automatically. And every week more radars, more projectiles, and more VT fuses came into operation. By the end of August, the cumulative effect of American production and British reorganization would reach its peak. A single day would record the destruction of 82% of the V-1s launched, not by luck, not by chance, but by the almost perfect functioning of a system built by thousands of hands, coordinated by dozens of factories, fed by applied science, and protected by absolute secrecy. Hitler's weapon of terror had found an opponent he had never considered, the collective intelligence of American industry. And for the Germans, the bewilderment was just beginning. In the next part, we'll explore how this frustration turned into despair within the Reich barracks, and why, for all its technical tradition, Germany couldn't even understand what was really defeating it. In the weeks following the collapse of the V-1's performance, the German command plunged into a cycle of failed attempts and contradictory conclusions. The growing failure of the campaign was so evident that emergency meetings began to take place daily at Luftwaffe headquarters and in the technical departments of the Reich. Frustration turned into paranoia. Max Wittel, commander of the V-1 operation, ordered a complete reassessment of the supply chain. Internal sabotage, tampering with components, error in fuel loads, gyro failures, Allied infiltration were suspected. Nothing was found. The releases followed the pattern. The bombs flew correctly, but they fell, day after day, without ever reaching their targets. The reaction was to escalate the variants. First, altitude changes. The V-1s were launched lower, then higher, no changes. Then, attempts to launch at random times, during the night or in periods of low visibility. The results remained unchanged. Then the strategy shifted to larger salvos. Up to 20 V-1s fired simultaneously, believing that saturation would confuse the British defensive system. It was useless. The rate of destruction increased proportionally. The pattern was clear. The British knew when and where to aim, regardless of the quantity or time. The only constant was failure. Technical intelligence officials tried to suggest that the UK had reorganized its air warning system, optimizing the response of the anti-aircraft batteries. Others proposed that British artillery had been given more accurate radars. But none of these hypotheses explained the observed phenomenon. V-1s destroyed without contact, exploding at distances noticeably greater than any conventional radius of action. The explosions occurred nearby, but not by impact, and it was exactly this detail that confused the engineers. Ballistic doctrine taught that the chance of hitting a small, fast, moving target was very low, and even if it were hit, the detonation would only be guaranteed by direct hit. The Luftwaffe's conventional munitions required this. The Allied data, however, suggested otherwise. Destruction occurred even without visible hit. It was as if the projectile itself decided the moment of the explosion. To Reich scientists, this made no sense. Reports sent out from the field began to include ambiguous terms such as spontaneous detonation close to the target or explosion without direct contact. The most creative assumptions began to emerge. Some believed that the British had developed optical sensors that adjusted the timing of fuses in real time. Others considered electromagnetic fields installed on the coast, but no one suggested proximity fuses. No one thought that the Allied projectiles had miniaturized circuitry, radio sensors, delayed activation batteries, and built-in transmitters. That was impossible, at least by Germany's industrial standards in 1944. America, however, did this on a daily basis. With 40,000 units manufactured every 24 hours, VT fuse production surpassed in volume and speed any equivalent weapon in the German arsenal. By way of comparison, the total production of V-1s over the entire war was lower than the monthly production of VT fuses at the height of American industry. If this number surprises you, comment below with a word that defines what you felt: absolute power, unbelievable, shocking data, or logistics wins. German frustration came to a head on August 26, when, even after attempts at tactical adaptation, more than 80% of the V-1s launched were destroyed. The machine that Hitler believed to be the ultimate instrument of retaliation had become a strategic burden. Maintenance, logistics, and production costs were rising. Internal confidence declined, and the effects on the enemy were almost nil. Worse, the morale of the Reich weakened in the face of the inability to explain what was happening. Intelligence could not capture a single Allied shell with an intact VT fuse. Counterintelligence did not detect suspicious movements in British factories, and no undercover source reported any new technology being used. The only plausible conclusion was, paradoxically, the one that no one dared to admit. They were being defeated by something they did not understand. This technical silence, this absence of explanation, was in itself an ideological collapse. Germany, which had built its military superiority on the myth of precision and advanced science, now saw its certainties crumble in the face of an enemy that combined science with volume, technology with mass production, intelligence with scale. The German tradition of unique weapons, unique designs, and genius solutions was being overtaken by a concept they never prioritized: integrated, replicable, predictable, and functional systems. It was not a war of brilliant ideas. It was a full-scale execution war, and while Berlin was mired in inconclusive meetings and reports, American factories were speeding up their treadmills. The ships carried more shells, the technicians calibrated more radars, and British anti-aircraft guns continued to function as synchronized clocks with invisible sensors. In the sky, the V-1 had become a target, no longer a threat, and what started as revenge was now just statistics. But the Germans did not yet know this. In the next part, we'll cross the frontier of the possible and look at the exact moment when the interception rate reached 82%, a day that would forever change the nature of modern warfare. The transformation did not begin with explosions. It started with numbers. By early August 1944, the interception rate of V-1s by British defenses was slightly over 50%. It was a quiet milestone, but one with devastating implications. What the Germans did not yet know is that this upward curve was not circumstantial. It was the mathematical effect of a system designed to scale, a model of warfare based on cumulative efficiency, calibrated to the millimeter to turn every unit produced into a tactical multiplier. The seed of the turning point had been planted weeks earlier, when the SCR-584 system was coupled to gun batteries equipped with VT fuses. This integration has created a new type of defense: automated, responsive, and, above all, predictable in its efficiency. Unlike gunners who adjusted their aim based on intuition or manual calculations, the radar did so in seconds. The target was tracked, the trajectory predicted, and the guns fired projectiles programmed to explode, not when the weather was ticking, but when the enemy was close enough. This proximity, captured by radioactive microtubes inside the ammunition, activated the detonator with unthinkable precision. But none of this would have worked without the invisible element that underpinned the entire operation: American industrial logistics. In Ohio, Crossley Corporation operated 24 hours a day, with more than 10,000 employees, many of them women, assembling and testing thousands of fuses per shift. Next to it, Sylvania Electric delivered reinforced vacuum tubes, originally designed for radios, but now adapted to withstand 20,000 Gs of acceleration. In Massachusetts, smaller factories assembled chemical batteries capable of activating after years of inactivity and lasting only as long as necessary to keep the circuit lit during flight. It was an engineering ecosystem designed to create a single piece of smart ammunition, and there was no waste. Each batch was tested, each failure recorded, each prototype perfected. The result? A weapon that was simple in appearance but technologically decades ahead of what the Third Reich could comprehend, and impossible to replicate with the infrastructure that Germany had in 1944. The British Anti-Aircraft Command, led by General Frederick Pyle, knew it possessed a special weapon, even though it did not know all the technical details of the VT. The orders were clear: position VT-fused batteries along the southern coast, prioritize V-1 targets, and manually track each unit fired. The goal was not only effectiveness, but absolute containment of secrecy. No shell could fall intact into enemy territory. All VTs launched against V-1s had inventory control, tracking, and immediate recall if they failed. This level of care explained why, despite tens of thousands of combat uses, no examples were recovered by the Germans. But the efficiency was in the data. Gunners reported something unusual. Shots that had previously required dozens of attempts to hit a flying bomb now resulted in hits on the first or second burst, and this was reflected in the weekly statistics. In July, the average interception rose from 27% to 43%. In the first week of August, it hit 58%. On August 20th, it exceeded 70%. Max Whittel in occupied France received the reports with growing unease. His command post in Châteaudun, interconnected with the Luftwaffe's technical intelligence network, compiled the data on the losses. Not only were they losing V-1s in large numbers, but they were losing with a consistency that defied any curve of randomness. Weapons without mechanical failure launched in good condition were being destroyed with mathematical regularity, and always on the coast. What had once been a transitional phase, the flight between France and London, had become the extermination zone. The only plausible explanation would be the existence of a new British defensive system. But which one? Analysis of the explosions observed in the high-powered binoculars indicated that the V-1s were not being hit directly. They were being surrounded by shrapnel, as if a nearby explosion had fragmented them in mid-air. But how to calculate a nearby explosion, in real time, accurately, in front of moving targets at more than 600 km/h? In Germany, experts insisted on classic explanations: ballistic probability, British tactical adaptation, human error. None of them dared to propose that the projectile would, thinking, that he could react alone without external adjustment. This was an idea that hurt the very principles of engineering rigidly established by the Reich, and therefore, it was discarded. Meanwhile, what was happening was an unprecedented efficiency curve. A single anti-aircraft gun with cast VT and SCR-584 guidance could accurately achieve results equivalent to 5 or 6 conventional guns. A system that once needed 2,500 rounds to shoot down a V-1 now did so with just 100. That meant less wear and tear, more control, and a multiplication of power. Every day, the defenses became more lethal, and every day, the Germans understood less what hit them. It was as if Germany was waging a war based on isolated technical genius, while the Allies operated in systemic synchrony between science, production, and the battlefield. The VT was not a miracle weapon. It was a cog in a much larger system, a model of warfare where coordination between university, industry, and the army replaced improvisation and faith in the perfect machine. And in this model, time worked against the Germans. For every day that passed, more American factories were converted to the production of the secret. By September, 40,000 fuses were being produced per day. The goal was clear: to saturate the defensive belts until the sky became impassable. And it was at this point that German officials began to consider the idea that there was something beyond physics at play. An internal report classified the results as technologically anomalous. Another mentioned, for the first time, the suspicion that the British were using a type of ammunition with intelligent response. It was a vague term, but it revealed the beginning of a cognitive turn. For the first time, there was a recognition, albeit whispered, that something unthinkable was being used against them. In the next part, we'll look at the exact moment when this suspicion turns to shock, the day when 82% of V-1s were shot down within hours, marking the definitive turning point of the Invisible War. On the cloudy morning of one of the last days of August 1944, when the clock on an SCR-584 radar post on the south coast of England struck shortly after 6 a.m., began what would later be remembered by Allied reports as the most effective day of anti-aircraft defense against flying bombs. On the circular radar screen, small echoes appeared in sequence from the English Channel side. A salvo of V-1 had just been launched from the German ramps in occupied France. At the British command post, the procedure was already known, almost routine. The radar operator identified the target, the SCR-584 system jammed automatically, the M9 analog computer calculated speed, altitude, and trajectory, and the firing solutions were sent, by cable, directly to the heavy artillery batteries, positioned along the coast. Within seconds, 90mm and 3.7-inch guns began to spin, raising their tubes with a timing that was only possible thanks to the combination of radar, automated calculation, and smart ammunition. By the time the first V-1s crossed the invisible line of the English coast, the gun belt was ready. Salvos of projectiles equipped with VT fuses began to cut through the sky, detonating not by time, but by proximity. in precise explosions around each flying bomb. On the German side, at an observation post attached to the Flak 155W regiment, long-range binoculars recorded a scene that did not fit in any ballistics manual. The V-1s maintained their trajectory until they were enveloped by a cloud of shrapnel in the air and then plummeted in flames toward the sea or the empty fields of the coast. Instead of isolated hits, observers witnessed an almost continuous sequence of mid-flight destructions. Throughout those hours of each group of bombs dropped, only a minority managed to break through the curtain of coordinated fire. What sounded to the British side as confirmation that the integration between radar and proximity fuses had reached operational maturity, to the German side took on the contours of a statistical nightmare. Interception rates, already high in the previous weeks, that day reached 82% destruction of the V-1s. In practical terms, out of every 100 flying bombs dropped, just under 20 managed to continue on to London, and even these would still be pursued by fighters and batteries further inland. In British Air Raid Command records, the day was described with a mathematical coldness that concealed its psychological impact. Number of V-1s detected, number engaged, number destroyed, number that crossed the belt, number that reached urban areas. For each column of figures there was a clear technological answer. Where thousands of shells were once fired to knock down a single target, now just over 100 was enough. Each VT fuse, which worked as expected, confirmed that American industrial investment, measured in billions of dollars and millions of units produced, was taking its toll on Hitler's weapon of revenge. In the maps placed on Max Witel's desk, however, these same figures appeared as a failure, deviation, inexplicable loss. Watching the lines that left the slipways towards England and ended almost all in the empty canal or in rural areas, the German commander silently saw the promise of a change of course in the war slip away, and the more he studied the reports, the more impossible the reality seemed before him. If the original calculations pointed to less than one hit in 10,000 artillery rounds with conventional fuses, how to explain a scenario in which almost 9 out of 10 flying bombs were shot down before reaching the target? The only logical response would be a radical change in the nature of enemy ammunition. But how to admit this in a system that, from the beginning, had underestimated American technological capacity? On the tactical level, what you saw at the British posts was the triumph of the system. Radars detected, computers calculated, pieces fired, VT fuses detonated, and the result was an almost continuous line of defense. A kind of invisible wall erected not by concrete but by radio waves, equations, and mass production. On the psychological level that morning, the German terror weapon was no longer seen as an uncontrollable threat, but as a manageable, statistically avoidable problem. Behind the scenes, Allied officers were already calculating based on interception rates how many lives were being saved daily, thanks to the use of VT. On the German side, the immediate reaction was the tense silence of the meeting rooms, where terminologies such as anomaly, widespread failure, and tactical inefficiency tried to hide an uncomfortable truth. The weapon that was supposed to demonstrate the Reich's technological superiority was being defeated by something as discreet as it was devastating. None of the officers present on that August afternoon knew that the secret behind that 82% loss day was not on the battlefield but on the assembly lines across the Atlantic, where American industry produced with almost mechanical regularity the small devices responsible for turning the V-1 into an easy target. And if the sight of their bombs falling in series was already humiliating, what they still did not imagine was that, even after the war, they would still not understand exactly what had defeated them. This forced ignorance would only be revealed when, in post-surrender interrogations, they heard for the first time incredulously the expression, VT proximity trigger. The greatest irony of that war is that at the height of the V-1 offensive, the weapon that destroyed them remained virtually invisible, both in the sky and in German intelligence reports. No field observer, no reconnaissance agent, no staff officer managed, during the entire campaign, to get his hands on a single intact VT fuse. This did not happen by chance. It was the direct result of a rare combination of industrial secrecy, logistical discipline, and operational control that the United States built around that small metallic cylinder that quietly rewrote Allied artillery statistics. In American factories, compartmentalization was almost absolute. Workers in Ohio, New Jersey, Massachusetts, or Pennsylvania assembled tiny components, welded wires, tested valves, filled battery capsules, and packed assemblies into numbered boxes without really knowing what they were creating. To many, it was just electronic warfare material, a term generic enough to hide the true nature of the project. The chief engineers and supervisors were given clear instructions. No parts could be discussed outside the sector. No technical notes could leave the perimeter. No drawings could circulate without military authorization. Instead of one big secret concentrated in a few hands, the United States divided the riddle into hundreds of small tasks, so that no one, alone, had the full picture of what the VT fuse was. This architecture of secrecy contrasted sharply with the German model, in which strategic projects such as the V-1 or V-2 relied on relatively small nuclei of scientists and officers concentrating knowledge and making the system vulnerable to failures and bombing. In the case of VT, even if one factory were destroyed, dozens more would continue to produce compatible parts, fed by the same standards, the same drawings, and the same test protocols. In British warehouses, control was equally strict. Each batch of ammunition equipped with proximity fuses was recorded, numbered, and distributed under direct supervision, with reports that specified how many shells had been fired, how many had missed, and how many had been picked up without detonating. Projectiles that did not explode in combat were considered as valuable as a secret document. Specialized teams were deployed to locate and recover each suspicious carcass in fields, forests, or beaches. If a VT shot fell into the sea, patrol vessels were activated to monitor the area, ensuring that no significant debris reached the enemy's hands. This level of logistical obsession alone explains why, throughout the entire campaign against the V-1s, Germany has never been able to examine a truly functional proximity fuse. There were occasions when Allied anti-aircraft shells fell on Axis-controlled territory, but in these cases the fuses were already destroyed by the impact, reduced to unrecognizable fragments. German laboratories, accustomed to dismantling enemy bombs and studying their mechanisms, came across only calcined scrap, without any clear clue as to what really made those projectiles so lethal. Technological blindness was reinforced by the Reich's own scientific prejudice. To many German engineers, the idea of miniaturizing radio valves to fit in an artillery shell, survive firing, and still function reliably seemed like a distant fantasy, something that might have been possible in 10 years, not in the middle of the 1940s. This judgment, based more on perception than verification, prevented German intelligence from seriously considering the hypothesis of proximity fuses. Reports such as the famous Oslo report, still in 1939, already mentioned British research in the area, but were shelved as misinformation or exaggeration. The historical irony is that while Germany was betting on spectacular visible weapons, giant rockets, flying bombs, jet fighters, the device that neutralized one of its major innovations was deliberately inconspicuous, hidden inside an ordinary projectile, without any outward signal to differentiate it from traditional ammunition. To a German observer, a VT shot was indistinguishable from a conventional fuse at a distance. The secret lay not in the form, but in the interior, in that small circuit that heard the return of the radio waves and chose the instant to kill. This combination of physical invisibility, industrial compartmentalization, and operational protection produced a rare effect in military history. A decisive system employed on a large scale without the enemy even being able to understand it during the year conflict. When, later after the surrender, officers such as W. Tell were confronted with intact and detailed VT fuses, many reacted not with admiration but with incredulity, stating that if they had seen it in 1944, they would have considered it an Allied forgery. They hadn't just lost missiles. They had lost the ability to imagine the level of integration between science and industry that the adversary had achieved. And it was precisely this failure of imagination that ensured that the VT remained invisible throughout the critical period, protecting London while at the same time quietly eroding German confidence in its own technical superiority. While generals discussed graphs and engineers recalculated probability tables, the key to the equation was on the other side of the ocean, in the hands of anonymous workers who fit the pieces of this technological mystery day after day. None of them would appear in intelligence reports, none would have their names mentioned in German military memos, but it was they who, without seeing a single V-1 in the sky, decided the fate of thousands, From the moment the first batches of VT fuses were delivered in sufficient quantity, the outcome of the V-1 campaign was no longer an operational unknown, but a matter of time and volume. Each new shift in American factories meant more smart shells on ships, more sealed boxes in British arsenals, and, inevitably, more V-1s shot down before they crossed the English coast. For the Reich, all this remained a faceless enigma. To anyone who looks back on the war today, it is clear that the decisive weapon was not the one that appeared in the propaganda speeches, but the one that never appeared in any photo. In the next part, this invisible force gains a face inside the American factories. While German engineers traced ballistics curves in closed rooms, across the ocean thousands of anonymous American workers ran their fingers through razor-thin wires, tiny valves and metal housings that would unknowingly decide the fate of Hitler's flying bombs. In red brick factories in Ohio, in metal sheds in Pennsylvania, on retrofitted assembly lines in New England, the sound of war was not that of explosions, but that of presses, welds, and hurried footsteps in 12-hour shifts. Many of these positions, especially in the electronics divisions, were held by women who had never set foot on a battlefield, but whose accuracy in attaching a filament or closing an electrical contact had more impact on the forehead than the firing of any rifle. At Ipswich, at the Sylvania plant, rows of workers adjusted vacuum tubes made to survive shocks of 20,000 times gravity, spinning at high speed, withstanding brutal temperatures, all so that, for fractions of a second, they would work inside a projectile that no one there would see in action. In Cincinnati, the Crosley Corporation pavilions, which had previously assembled home radios and refrigerators, were cut into dedicated sectors. One group only molded casings, another only assembled contacts, another only tested, creating an industrial cadence in which each worker was an indispensable cog in an invisible gear. Most knew only that they produced something top secret, a component that needed to work the first time, because there would be no second chance on the battlefield. No one received full explanations, no notice board described the proximity fuse, and this protected ignorance was an additional layer of strategic armor. While the Reich buried tens of thousands of prisoners in tunnels to forcibly assemble flying bombs, the United States paid overtime, offered hot coffee in cafeterias, and called on housewives, students, and farmers to join this silent army of manufacturing with quick training. The individual stories almost never appeared in the newspapers, but on each bench there was someone mentally counting how many screws were left in the shift, how many parts needed to pass the vibration test, how many errors could be tolerated before a supervisor noted a deviation in the report. In practice, these ordinary hands were writing living equations. Every weld done correctly increased the chance of a V-1 being destroyed. Every component refused prevented a combat failure. Every approved batch meant fewer Nazi explosives over civilian neighborhoods in London, Antwerp, or Brussels. Salaries were modest. Fatigue was constant. But the sense of purpose grew with each public communiqué that spoke of new secret weapons, helping to protect ships in the Pacific and cities in Europe. What the communiqués didn't say was that, often, this secret weapon was just a small cylinder threaded onto the end of a projectile. On certain peak days when American production of VT fuses reached 40,000 units daily, this meant that in 24 hours, the United States produced more proximity devices than Germany could put V-1 into operation for entire weeks. If this difference in scale surprises you, remember that we are talking about an industry capable of delivering, in a single month, more proximity fuses than the total number of V-1s built by the entire Reich. If this shocks you, write in the comments. Logistics wins or shocking data, and see how the war is often decided very far from the front line. For the workers, however, the world was measured in small details. The correct temperature of the soldering iron, the smell of the heated insulator, the short noise of an approved part on the test bench, the time card stamped at the end of the night before taking the tram back home. Some kept newspaper clippings about ships saved in the Pacific, or about London boroughs spared after V-1 attacks, unaware that the discreet lines talking about improved anti-aircraft artillery were largely the direct result of the almost mechanical repetition of their own gestures. Sergeants and Allied officers, when visiting the factories for motivational speeches, spoke of revolutionary weapon and saving lives at the front, but they could rarely explain how such a fragile circuit survived the firing of a cannon. The answer lay in the union between laboratory and production line, something that authoritarian regimes, trapped in internal secrets and personal rivalries, were never able to imitate. For every reputed engineer who appeared in reports, there were hundreds of nameless technicians tuning instruments, calibrating gauges, stamping inspection forms, ensuring that the pattern repeated itself flawlessly, and that every box sent to England carried exactly the same deadly reliability. When years later, military historians calculated that the application of VT fuses against V-1s reduced civilian casualties in London by as much as 4 or 5 times compared to projections based on conventional ammunition, the names of most of these workers were still lost in payroll files, timesheets, and yellowed factory photographs. The victory, seen from afar, seems to have been won by graphs, production curves, and reports from the general staff. Seen up close, it was built by ordinary people who, repeating the same gestures hundreds of times a day, turned electronics into shields, radios into weapons, and fatigue into strategic statistics. While German officials wrote in tense reports that there is no satisfactory technical explanation for the losses, in some wooden shed in the United States, a young woman was adjusting the same copper contact for the 1,000th time, not knowing that that small metallic click would mean weeks later, one less V-1 in the sky over Europe. In the invisible part of the war, they had already won. All that was missing was for someone, years later, to put the numbers together and understand that that human chain of anonymous workers and technicians had done more to break Hitler's revenge than many generals, paving the way for the brutal comparison between the two industries that the world would see next. When you put the German V-1 industry side by side with the American effort dedicated to VT fuses, the war ceases to look like a duel of arms and becomes, clearly, a confrontation between industrial systems. Germany bet on the V-1 as a weapon of strategic effect, but its production, despite the high numbers by Reich standards, remained stuck in an almost artisanal, centralized, fragile model. The assembly of the V-1 required specific facilities, large components, complex assembly lines, and, above all, depended on forced labor in underground factories like Mittelwerk, where prisoners were subjected to brutal conditions to maintain the minimum rate of delivery. Each V-1 cost something around 5,000 Reichmarks and required strategic materials, high assembly time, and constant maintenance of the launch infrastructure. The American VT fuses program, on the other hand, followed another logic. Instead of concentrating effort on a wonderful weapon, the United States took what already existed, cannons, radars, cluster munitions, and multiplied their effectiveness with a relatively small component, replicated en masse. While the Reich struggled to complete tens or hundreds of V-1s a week, American factories like the Crosley Corporation alone delivered thousands of fuses a day, integrated into a network of more than 100 industrial plants working in sync. In financial terms, the contrast is even more stark. The unit cost of a VT fuse started out high, in the hundreds of dollars, but as production accelerated and processes were standardized, it dropped to less than $20 per unit, allowing millions to be manufactured without strangling the war budget. Germany, on the other hand, has never been able to significantly cheapen the production of the V-1, which is tied to places vulnerable to bombing, poor supply routes, and chronic shortages of raw materials. While the VT program fed on a mobilized market economy, with private companies integrated into a government-coordinated effort, the V-1 program relied on coercion, improvisation, and logistical tinkering. In terms of scale, the disparity is almost impossible to overstate. By the end of the war, the United States had produced more than 20 million VT fuses, a number that far exceeds the approximately 25,000 V-1s built by the Germans. This means that in many months, the American production of proximity fuses alone exceeded the entire volume of flying bombs manufactured by the Reich in years. And unlike the V-1, each VT fuse was not a standalone weapon, but a power multiplier applied to thousands of artillery pieces in various theaters of operation, from the English Channel to the Pacific. The American model proved that the true strength did not lie in the isolated sophistication of a project, but in the ability to transform science into a serial, repeatable, transportable product. Germany has built a weapon of revenge. America has built a system where universities, laboratories, industries, and the armed forces spoke the same language of specifications, deadlines, and quality standards, generating a constant flow of innovation applied directly to the front lines. The Reich, obsessed with the search for decisive weapons, dispersed resources in projects that rarely made it past the prototype stage in significant quantities, while the adversary consolidated few solutions but mass-produced them. In the human field, the moral abyss also translated into efficiency. American workers, although tired, acted with training, financial incentive, and a sense of purpose. German enslaved workers, exhausted and poorly fed, produced in conditions that generated defects, delays, and silent sabotage. The result of this difference appears not only in tons of steel or in production charts, but in the final statistics of the campaign. The V-1 program drained millions of marks, consumed valuable materials, and claimed prisoners' lives, only to be neutralized by fuses that cost less than $20 and were fitted together, almost anonymously, in 90mm ammunition. Modern warfare showed its true face there. It is not the winner who has the most impressive weapon on paper, but the one who can feed the front lines every day with reliable, cheap, and available technology. When post-war German officials were confronted with these figures, many admitted that even with more time the Reich would hardly be able to match American industrial capacity, and it is precisely this confession that opens the door to the next inevitable question. How did this systemic superiority, which had already defeated V-1, begin to translate in practice into concrete victories on the battlefield, and lives saved in the cities that Hitler had promised to destroy? When the V-1 interception rate consistently exceeded the 70% mark and peaked at 82% in a single day, the impact at the front ceased to be a technical datum and became a concrete change in the landscape of war. London, which weeks earlier had been living under the constant sound of pulsating engines and sudden explosions, began to experience something that seemed almost like a miracle: intervals of silence. The damage maps, used by the British Anti-Aircraft Command to measure the devastation, showed a curious curve. The number of V-1s launched remained high, but the number of impacts in urban areas shrank month by month. Neighborhoods that at the beginning of the campaign were dotted with craters began to record only sporadic falls, often in empty fields or in the sea. The population, which identified the V-1 by the characteristic sound of the engine cutting through the sky, followed by the deadly silence before the explosion, began to hear this sound less frequently. The daily terror was replaced by a cautious sense that something, at last, had come between London and Hitler's vengeance. This barrier was not visible like the concrete of a shelter, but it was just as real. A combination of SCR-584 radars, M9 computers, and VT fuses synchronized by a logistics chain that linked American factories to British batteries. At the operational level, the Anti-Aircraft Command responded to early evidence of success with what the United States had demonstrated to be its greatest virtue: standardization and expansion. Industries where VT performance was better were used as a model for others. Operating manuals have been rewritten, highlighting best practices for tracking, engagement, and ammunition economy. Less efficient regiments received additional training, with observers and instructors coming directly from the zones with the highest kill rate. In strategic terms, the result was that, in a few weeks, the British defense against V-1 ceased to be a patchwork quilt and began to behave as an integrated system, with predictable and increasing performance. The Royal Air Force, which had initially taken on much of the brunt of interception with fast fighters attempting to shoot down the low-flying flying bombs, was gradually able to shift its units to other tasks, as VT-equipped ground artillery took on most of the defensive load at a lower cost in lives and aircraft. On the German side, the effect was the reverse. Each wave of V-1s lost represented not only tons of explosives that did not reach the target, but also a clear message to planners in Berlin that the bet on the weapon of revenge was becoming a strategic drain. German intelligence reports from the time show this deterioration. Initial enthusiasm, fueled by predictions of British morale collapse, gave way to memos that spoke of significantly reduced effectiveness and the need to reconsider resource allocation priorities. In cold numbers, of about 9,500 V-1s launched from land ramps against Britain, just over 2,500 hit the London area. The rest were lost, shot down, or dropped before achieving any significant military value. American proximity technology, supported by a production system that poured tens of thousands of fuses a week onto the front lines, turned the V-1 into a negative, cost-effective weapon, expensive to produce, expensive to launch, cheap to destroy. Demoralization was not restricted to the enemy. Within the German military machine itself, Officials began to question, albeit quietly, the insistence on wonder weapons programs at the expense of investments in essential defenses, such as fighter jets, anti-tank ammunition, and fuel. Some post-war documents record that anti-aircraft artillery officers even considered the sending of V-1s a gift to the British, a bitter expression that epitomized the perception that the industrial, logistical, and human effort invested in those bombs was literally being burned in the sky over the Channel. For the Allied command, however, the fight against the V-1 was more than a defensive campaign. It was a laboratory of integration between technology and strategy. The VT's success against flying bombs offered a real-time validation that the American bet on systems, and not on isolated weapons, was the right path. The experience accumulated in the coordination between radar, analog computing, heavy artillery, and smart ammunition would be applied in other contexts, in the European theater, and especially in the Pacific, where the same VT fuses would help protect ships against Japanese air attacks and kamikazes. Each V-1 shot down was not just an impact averted, it was more of a proof of concept for a model of warfare in which industrial advantage decided what was or was not possible on the battlefield. On the political level, the relative preservation of London has had profound effects. A ruined city, under constant bombardment, would struggle to sustain its role as an Allied command center. A wounded but operational London continued to house offices, ministries, intelligence centers, and foreign delegations. The message sent to allies and enemies was clear. Neither the Blitz nor the weapon of revenge had succeeded in bending the British capital, and that in large part, thanks to circuits built thousands of miles away, in factories that would never smell gunpowder. By the time the German command finally began to admit that the V-1 campaign would not achieve the promised results, the damage was already done. Resources that could have been invested in defenses, supplies, or conventional equipment were diverted to sustain ramps, produce bombs, and maintain a launch infrastructure that, each day, delivered less strategic return. By the end of 1944, on the basis of a cold analysis, the weapon of revenge had become a symbol of industrial waste, of misjudgment, and above all, of the inability to understand the logic of modern warfare. The United States and the United Kingdom had converted science into a practical tool. Germany had turned technical brilliance into an operational dead end. And yet, the story of the V-1 and the VT fuses does not end with the London figures. There was a second, more subtle effect that began to take shape. The lesson that the real battlefield became as important or more important than the trenches, the terrain of intelligence and technological imagination. This lesson would become painfully clear when, even after the surrender, German scientists and officials finally saw with their own hands what they had never been able to grasp during the entire campaign, and were forced to admit the size of the gulf that separated them from their adversary. When the effectiveness of the V-1s plummeted and the Allied interception rate rose to levels that contradicted any known calculation, the German intelligence machine was rallied at all levels, in a desperate attempt to find an explanation that would not call into question the Reich's own faith in science. Reports began to pour in from flak batteries, coastal observation units, and technical teams tasked with monitoring the trajectory of the flying bombs, all repeating the same uncomfortable finding. The revenge weapon worked perfectly in internal tests, but failed humiliatingly whenever it crossed the English Channel. At first, the most comfortable explanation was sabotage. Investigators were sent to factories, assembly lines were inspected, components were dismantled piece by piece, prisoners were interrogated with increasing brutality, but no systemic flaws were found that could justify the carnage of V-1s shot down far from London. The analyst's mental structure, shaped by years of confidence in German precision, rejected the simplest and most humiliating hypothesis, that the enemy had developed a technology that the Reich considered, in its own laboratories, to be unfeasible for at least a decade, something belonging to the future rather than the present battlefield. The irony of this story is that the solution was ahead of them, cited in old reports, mentioned in rumors about pre-war British research, but systematically dismissed as misinformation. If you are enjoying unraveling this type of strategic blindness, show your support, like the video, and subscribe so we can continue to bring you analysis like this. Within military intelligence structures, totalitarian logic imposed invisible filters. Reports that suggested superior Allied capabilities were met with skepticism. Analysts who dared to propose bold explanations were seen as alarmist, and any hypothesis that implied admitting technological backwardness in relation to the United States tended to be softened or simply ignored. Meanwhile, on the other side, the American approach went in the opposite direction. Problems were brought back to the labs. Engineers sat with field officers. Performance statistics fueled design changes. And doctrine was treated not as dogma, but as something constantly adjustable in light of new data and industrial opportunities. In Germany, intelligence tried to fit the phenomenon of V-1s shot down into known models, recalculating probabilities, revising dispersion parameters, checking for supposed improvements in British marksmanship. But all this math revolved around a fundamental error. It assumed that Allied anti-aircraft shells were still essentially blind shells. No German report seriously considered that each shot could carry within itself a small circuit, capable of emitting signals, sensing the return in the metal hull of the target and deciding, on its own, when to explode. This idea was so far removed from the industrial reality of the Reich that it was not part of the mental horizon of its own specialists. The totalitarian system, which in theory centralized information, in practice created bubbles of isolation. High-level scientists did not always have raw access to field failures. Frontline officials were not fully informed about design limitations, and the pressure for good news distorted the reading of the numbers arriving in Berlin. The American effort, on the other hand, was fed precisely the opposite. Reports of failures were valued, serial destructive tests were encouraged, and each fuse that did not work as intended became raw material for a chain of improvements that passed through universities, military research centers, and the factory floor, until the rejection rate fell to minimum levels. This difference in organizational culture explains why, even with brilliant scientists on its staff, Germany remained blind to the true nature of what it faced. Their best brains spun inside a rigid conceptual box, while the adversary tweaked, tested, errored, corrected, and, above all, produced at scale what he knew worked. When, on rare occasions, German agents intercepted unexploded Allied ammunition, what they found were deformed casings, unrecognizable fragments of components, remnants of broken tubes and burnt wires, insufficient material to reconstruct the mechanism, or to convince skeptics that they were dealing with something qualitatively different from the known fuses. Without access to a piece of integrity, the Reich's technical intelligence continued to operate in the dark, building theories around more efficient radars, supposedly finer time calculations, or unbelievable improvements in British fire discipline, always attributing the failure to incremental factors and never to a hidden revolution in enemy electronics. If, at some point, a bolder officer suggested the possibility of proximity fuses, this hypothesis succumbed to Germany's own industrial limitation. Admitting that the enemy dominated something that the Reich could not produce meant, in practice, acknowledging that the war had been taken to a terrain where the propaganda of German technical superiority did not hold up. Meanwhile, in the United States, the flow of information followed a path that authoritarian regimes rarely tread. Civilian scientists were invited to read field reports. Military personnel participated in laboratory tests. Political authorities received technical explanations in accessible language. And this created a virtuous cycle between decision-making, experimentation, and mass production. Behind the apparent immediate success of the VT fuses against the V-1, there was therefore a profound structural difference. On the one hand, an intelligence bound by ideology, fear of admitting weaknesses, and inability to imagine technologies outside its own repertoire. On the other, a system willing to test the improbable and transform what worked into an industrial standard. The failure of German intelligence in this context was not only not to discover the VT, it was not realizing that the war had changed its axis, that the real advantage lay in the ability to integrate science, factory, and field in a continuous circuit, something that the Reich with its rigidity never managed to build. This blindness would only be exposed after the surrender, when German scientists and officers placed in front of a VT fuse dismantled on an interrogation table, heard the explanation, and had to confess the delay of a decade in relation to the enemy. The engineering behind the VT fuse was not an isolated stroke of genius, but a demonstration of how science, when linked to an organized industry, can change the fate of a war. Inside a metal casing the size of a fist, American engineers were able to fit a small radio transmitter, a receiver, detonation circuits, chemical batteries, and miniaturized vacuum tubes capable of surviving forces that no civilian equipment had ever faced. When the projectile exited the barrel of the cannon, It was subjected to about 20,000 times the gravity, rotating at tens of 1,000 revolutions per minute. Even so, when it got close to the target, this device was still able to emit signals, pick up the echo in the body of a V-1, and trigger the detonation at the exact point where the fragments would be most likely to destroy the flying bomb. This miniaturization did not come out of nowhere. It was the result of years of research into radio, home electronics, and communications equipment that, after 1941, were suddenly placed under a new rule. Anything that could hear, emit, or measure signals could be weaponized. In the laboratories of the Johns Hopkins Applied Physics Laboratory, and at centers such as Bell Labs, scientists and engineers have tested hundreds of different configurations of tubes, coils, crystals, and batteries, always with one unyielding condition: survive the firing of a real cannon. Prototypes that looked promising on the bench were rejected in the first field test if any component broke or failed to fire at the right time. This culture of mass-destructive testing is in direct contrast to the German mindset, which is often geared towards protecting sophisticated prototypes rather than breaking them until they understand their real limits. The industrial quality of the VT program also deserves attention. Each batch of fuses went through several layers of inspection, including electrical tests, simulated vibrations, temperature cycling, and actual shots at proof polygons. Samples were randomly taken from the boxes. If failure rates rose beyond a few percentage points, entire production lines were overhauled, processes were recalibrated, and entire pieces of machinery could be replaced. The goal was not just to deliver quantity, but to ensure that each fuse was reliable under extreme conditions. In terms of engineering, the challenge was contradictory. The device needed to be sensitive enough to detect the return of radio waves in a relatively small object, but robust enough to withstand mechanical pressures that would destroy laboratory equipment. This required the creation of miniaturized vacuum tubes with reinforced structures, improved materials, and manufacturing processes that deviated from the civilian standard. The batteries, in turn, had to remain inert for years in damp and cold deposits, but activate instantly after firing, when acceleration forces activated their internal elements. None of this was magic. It was applied engineering in a methodical way. Contrary to the romanticized narrative of a sudden secret weapon, VT was the result of a chain of technical and industrial decisions made under pressure, but anchored in rigid measurement and improvement procedures. Real field statistics went back to the labs, where teams compared predicted behavior with observed outcomes, adjusting components, sensitivities, and trigger limits. There was a continuous cycle between combat and design, something that Germany could hardly reproduce at that stage of the war. Pressured by constant bombing, shortages of raw materials, and a political system that did not tolerate bad news or deep revisions of doctrine. From a technological point of view, the greatness of the VT lies not only in the fact that it does what German engineers considered impossible, but in the fact that it does it millions of times, with an acceptable failure rate for massive use in the field. A revolutionary prototype is an intellectual feat, a revolutionary device that can be manufactured at scale by ordinary workers is a triumph of production engineering. It was precisely this combination that allowed each factory in the United States to become an extension of the laboratory, faithfully reproducing what the scientists had conceived. For the German scientists who, in the post-war period, finally had access to a complete VT fuse, the reaction was almost unanimous: disbelief. Some have stated that if they had been shown that device in 1944, they would have assumed that it was a propaganda montage. They could not conceive how such small vacuum tubes could withstand the shocks of firing, nor how such compact batteries could remain active only for as long as necessary. This astonishment reveals something greater than a simple difference in equipment, reveals a difference in the scale of technical imagination and the ability to transform ideas into repeatable processes. At the heart of VT was also a modern systems engineering concept. The device did not exist in isolation, but as part of a larger architecture that included radars, analog computers, field employment protocols, and timed supply chains. Each fuse was designed to converse, as it were, with the rest of the system, ensuring that lethal power depended not only on a single link, but on the sum of all of them. In this sense, VT engineering was the ultimate expression of what modern warfare would become, a competition between complex networks, not just individual weapons. By observing this reality, It is clear that the shooting down of 82% of the V-1s in a single day was not a stroke of luck by artillery, nor a simple response to superior training. It was the end product of thousands of design decisions, millions of parts produced to tight tolerances, and an entire society willing to turn its accumulated knowledge into concrete technical advantage. It was not just a matter of winning a battle in the sky of England, but of demonstrating that in a global conflict, organized engineering can be worth more than any isolated heroic gesture. And it is precisely this conclusion that makes the German reaction in the post-war period all the more revealing. When it finally confronted the secret it never understood. Seen from a distance, the victory over the V-1 seems just a curious story of technology against technology. But when you look closer, it reveals something much deeper, a clash between models of society. On the one hand, a totalitarian regime that believed that the genius of a few, supported by iron discipline and terror, would be enough to compensate for scarcity, improvisation, and internal brutality. On the other, an industrial democracy that, with all its flaws, managed to mobilize millions of free people around a common goal, transforming laboratories, small workshops, and large factories into extensions of the same project. The difference was not only in the production charts, but in the way each system treated human beings. Germany built its weapons of revenge and forcibly dug tunnels among the corpses of prisoners, in the midst of darkness and fear. The United States manufactured its VT fuses in lighted warehouses, with unions negotiating working hours, families waiting at the door of the factories, the government asking for sacrifice but also promising wages, rights, and a future after the war. The industrial quality that made a fuse resist 20,000 times gravity was not just a technical fact. It was the consequence of an environment in which error could be reported without fear of political punishment, in which a rejected part did not mean betrayal, but an opportunity to improve the process. German artisanal perfectionism, which admired brilliant prototypes and unique machines, ran into the limit of a world in which each unit needs to be replicated thousands, millions of times. In this world, the obsession with isolated, wonderful weapons became an expensive luxury, while the adversary bet on what seemed less glamorous but decisive: standardization, repetition, incessant testing, statistics. Morally, the V-1 campaign exposed a tragic paradox. The more the Reich invested in a weapon built at the expense of enslaved lives, the more that weapon was nullified by devices produced by workers who could go home after their shift, who had a name, a family, an address, and who did not know at that moment that they were saving other families on the other side of the ocean. Modern war, in the light of this history, ceases to be just a field of individual heroism and becomes a mirror of the collective capacity to organize knowledge, energy, and character. It is not only the one who shoots the best, but the one who is able to align engineers, workers, politicians, and soldiers in the same line of moral and technical production. That is why, when the VT fuse began to transform near hits into systematic hits, it was not a question of American luck, but of the end point of a process in which industrial democracy managed, for the first time, to impose its logic on the tyranny of improvisation and propaganda. The irony is cruel. The regime that preached racial and technical superiority was defeated in this respect by assembly lines that mixed immigrants, women, African Americans, simple people who would never be accepted in the ideal of purity, preached by the enemy, but who, with patience and discipline, welded the pieces of an invisible weapon that dismantled the Führer's revenge. At the same time, this technological victory should not be romanticized as if the machine, on its own, had a morality of its own. Those who decided to use the VT to protect cities, and not just to increase destructive power, were commanders who saw value in preserving the rear guard, in caring for civilians, in the idea that keeping London standing meant more than protecting buildings. It meant keeping alive a society capable of resisting. The ethical contrast appears even in the post-war period. While Germany would carry for decades the weight of having buried its intelligence in mountains of concrete and slave labor, the United States would celebrate its factories as symbols of opportunity, although it would not always recognize individually who, in fact, paid the price of industrial effort. The lesson that emerges from the trajectory of the V-1 and the VT fuses is hard and clear. In modern warfare, morality is not an accessory of technology. It is embedded in the way technology is produced, distributed, and used. Regimes that treat people as disposable parts end up discovering sooner or later that they have built weapons with rotten foundations. Societies that, despite their contradictions, preserve spaces of freedom, debate, and course correction tend to generate more resilient, more adaptable, and ultimately, more effective systems. The day 82% of the V-1s were shot down in a single strike cycle was not only a victory for physics and electronics, it was a quiet assertion that collective intelligence, organized, free, and disciplined, can defeat the isolated brilliance of any dictatorship. And even so, the world had yet to see how this superiority would be revealed, without filters, when the defeated were finally invited to look, with their own hands, at the small metallic cylinder that had put in check all their belief in invincibility. When the war ended and the guns fell silent, the VT fuses continued to work, no longer in explosions, but as a silent reference in reports, laboratories, and military classrooms. For many soldiers and gunners, they were just special ammunition, one of many boxes marked with codes. For post-war engineers and strategists, they became a milestone, proof that the combination of radar, electronics, and mass production had ushered in a new era of combat. From a technical point of view, the principle of VT was simple: detect proximity and react. From a historical point of view, he redefined what it meant to aim at a target. In the years that followed, virtually all modern air defense systems drank from the same source. Radar-guided surface-to-air missiles inherited the logic of the sensor that decides when to explode. Radio altimeters, used in civil and military aircraft, applied the same idea of measuring distance by signal reflection. Even cluster artillery ammunition used in the Cold War carried, in more advanced versions, direct descendants of the concept of proximity. Electronic warfare, still embryonic in 1945, found in the legacy of the VT a concrete example of how invisible waves could define who lived and who died. Curiously, the recognition of this revolution did not come immediately. For years, public fame has focused on flashier weapons: the V-2, jet fighters, the atomic bomb itself. The VT was in the shadows, protected initially by secrecy and then eclipsed by the grandeur of the nuclear explosions. It wasn't until analysts began to compare costs, results, and strategic impact that the true importance of that small metal cylinder emerged. They realized that without the VT, not only would London have suffered far greater casualties, but the entire doctrine of fleet defense in the Pacific would have been forced to operate under permanent risk of collapse. In the post-war period, reports from the United States Navy pointed to the proximity fuse as one of the decisive factors in countering air attacks, especially against naval formations vulnerable to low dives and, later, suicide attacks. The same logic that had brought down V-1s over the Channel began to protect destroyers, cruisers, and aircraft carriers in distant seas. Instead of expecting a direct hit, defensive artillery could saturate the space around enemy aircraft, detonating projectiles at the optimal distance to turn approaches into clouds of shrapnel. The relationship between science, industry, and human survival became, there, inescapable. The legacy of the VT also shaped military training. Gunnery officers began to be instructed not only in classical ballistics, but in systems integration, radar, communication, automatic calculation, and smart ammunition. The figure of the isolated gunner, relying on aim and experience, gave way to the operator of a complex system, capable of reading screens, interpreting echoes, and relying on mechanical algorithms. It was the anticipation, in analog form, of what decades later would be known as network warfare. Each artillery piece ceased to be an island and became a node in a larger set, powered by sensors and coordinated by command centers that thought in terms of area, not individual target. The influence extended far beyond the battlefields. At civil airports, radio approach systems and altimeters based on principles similar to that of the proximity fuse have increased the safety of landings and takeoffs, especially in conditions of low visibility. In satellites and space probes, the idea of measuring distance by signal return time has become an everyday tool. The same reasoning that had dropped a flying bomb over the Channel now helped commercial aircraft land safely and allowed robotic spacecraft to navigate in a vacuum. The boundary between military and civilian technology, once again, proved to be porous. At the same time, the historical recognition of the VT was slow to arrive. Many of those who participated in the program worked for decades without being able to talk openly about what they had done. Reports remained classified, Photos were stored in archives, and the very designation, variable time, continued to obscure the true principle of proximity. It was only when documents began to be released, starting in the late 1950s, that scholars began to see the VT program as one of the most successful experiences in the integration of science, industry, and the military. In a world increasingly obsessed with nuclear weapons, the story of that little fuse served as a reminder that not every turn of war is accompanied by a flash on the horizon. From a moral point of view, this legacy raised uncomfortable questions. If a relatively cheap innovation could save so many lives in London and at sea, what other technologies, if produced and applied with the same determination, could have reduced suffering in later conflicts? The history of the OT suggests that the line between destruction and protection lies not just in the potency of the weapon, but in the purpose and context in which it is employed. The same circuit that could be adapted to increase the lethality of an offensive was initially used to protect cities and fleets. This choice was not neutral, but the result of specific political and strategic decisions. Ultimately, the proximity fuse showed that the real secret weapon of industrial democracies lay not just in brilliant laboratories, but in the ability to turn theory into stable production, and stable production into concrete effects on the battlefield. He demonstrated that the future of warfare would be less about individual heroism and more about the competence of entire systems, where every operator, every technician, and every engineer played a role as vital as that of the soldier on the front line. When looking to the past, many historians see in the VT a kind of bridge between the age of gears and the age of circuits. And for the German scientists who only knew it disassembled, on interrogation tables after the surrender, that bridge came with humiliation. They realized that they had lost not only the V-1 campaign, but an entire decade of technological and industrial advancement, and everyone would remember it. In the end, when the files were opened and the numbers were put side by side, what was seen was not just the collapse of a gun, but the collapse of an entire belief. Germany had bet that the brilliance of its engineers, concentrated on the V-1, could make up for the lack of steel, fuel, and time. And he discovered the hard way that the real strength of modern warfare was not in the perfect weapon, but in the gear that faces it every day, without glamour, without propaganda, only with precision and repetition. In practice, 82% of the flying bombs dropped in a single day on London were destroyed by projectiles that carried, within them, an invisible intelligence created on the other side of the Atlantic, proving that the central thesis of this story is implacable. It was the industrial, logistical, and technological power of the United States, integrated into British defenses, who doubled Hitler's weapon of revenge, and not any isolated gesture of heroism. The V-1, heralded as a symbol of German technical superiority, ended as a demonstration of its strategic blindness. Every bomb produced at the expense of slave labor was neutralized by a fuse built by free workers. Each carefully camouflaged launch pad faced a system that combined radar, automatic, calculation, smart ammunition, and an uninterrupted flow of boxes from factories where no one could see the sky of war. But they all touched, with their own hands, what he would become. The great lesson of this confrontation is brutally simple and, at the same time, profoundly universal. In modern warfare, logistics determines strategy. The ability to produce and integrate systems is worth more than any brilliant plan drawn on a map table. It doesn't matter how sophisticated a regime's weapon seems if it can't be sustained, fueled, protected, and confronted by an adversary capable of turning science into process and process into routine. The Germans tried to win by the genius concentrated in a few dazzling projects, but they were defeated by a model that accepted the humility of numbers. Test, make mistakes, correct, produce, standardize, repeat. While the Reich was still debating whether proximity fuses were technically possible, American factories were already producing tens of or thousands of them a day, and each of them was a failure sentence for a V-1 that, on paper, seemed invincible. This story also reveals another uncomfortable truth. Volume trumps tactics when volume is guided by intelligence. It is not just a matter of having more, but of organizing this more in coherent chains in systems that talk to each other, making each radar, each cannon, each worker a conscious part of a larger strategy. This is what transformed the absurd statistic of one hit in every 10,000 rounds into a routine in which 100 well-guided projectiles were enough to bring down a flying bomb, And this not because the gunners became miraculously more skilled, but because the ammunition, inside, began to carry the sum of millions of hours of work and research. Post-war, when German scientists were finally placed in front of a dismantled VT fuse and heard the full explanation of how it works, many reluctantly admitted that they were a decade behind their adversary. One of them, summing up the humiliation of seeing his own faith broken by a metal cylinder the size of a hand, would have said, "We thought of fighting soldiers, but we were defeated by workers, engineers, and trucks," a phrase that perfectly condenses the central irony of this narrative. If you have come this far and believe that stories like this help to see the war beyond the myths, support the research and the search for historical truth. Leave your like, subscribe to the channel, and share this video so that more people understand how industry, science, and organization decided the fate of entire cities. And it says below in the comments, what was the most shocking data for you? The production of more than 20 million fuses, the 82% of V-1s shot down in a single day, or the German inability to capture a single intact specimen. Also activate the notification bell so you don't miss the next devastating historical fact, because, like this one, many others were hidden behind numbers, secrets, and reports that almost no one read, but that changed the course of the century. The history of the V-1 and the VT fuse shows that the real battle was not only fought over the English Channel, but on the drawing boards of engineers, on factory machines, on the decisions of commanders who chose to invest in discrete systems instead of spectacular weapons and who, in the end, saved more lives than any discourse could admit at the time. She reminds us that whenever someone relies too much on a miracle weapon, it's prudent to ask what system is behind it, and which system works quietly to bring it down. Don't go away yet. Listen to the next real story that will appear on the screen, because this war of engineers, workers, and commanders continued in other skies, in other seas, and in other campaigns in which invisible technology spoke louder than uniforms and flags. Always remember, logistics determines strategy. Watch the next video here on the channel with another incredible story and see how, on different fronts and with other weapons, the same silent law of modern war continued to apply, the law that whoever dominates the backstage of production ends up sooner or later ruling the main stage of history.